All right, everybody. This is Mr. Aynesworth at Great Oak High School, and we are in financial algebra here in Chapter 9, Section 9, working on linear programming and optimal outcomes. And we're going to be working on problem number 9. And if you notice here, I have my reformatted lesson on the left, and I have the original workbook on the right. So on the right, in the workbook, it steps out the ways to think about the problem, which is not usually given. Okay, we're not going to be testing that way. I'm not going to give you all these hints and ideas. What we need to do is learn how to take this word problem and translate it and organize it in form of a table so that we can actually write the system of constraints and optimize the problem. All right, but we're going to use the workbook here just as a tool to help us get organized in the problem. So let's go ahead and start working on it. Let's read it, of course, and annotate it, and then we'll go back to the workbook here in a minute. So get out your red pens and highlighters. Here we go. Okay, so the first thing we do is we start reading the problem to understand it. Okay, this is an industry problem. Industry City is a company here. It's a startup company that produces picnic table sets that are made from recycled metal. Okay, right now, Industry City has two big clients, and their clients are River Cottages and Oceanside Resorts. Okay, and notice that they are in the table. Okay, River Cottages needs at least 60 tables. Ooh, look at that! It needs at least 60 tables. Well, guess what? That is it's going to be a constraint here because it says that it needs. River Cottages, it needs at least 60 tables. Whereas, if you read on a little bit here, it says Oceanside Resorts needs at most 150 tables. And what we need to do is kind of organize these ideas, and we need to interpret what does it mean to be at least 60. All right, what does it mean to be at most 150? So these become inequalities. And one's a min and one is a max, and you need to be able to interpret these as numbers here. So before we get started here, let's just read the workbook here and just read part A. And so part A here, it says let X represent the number of tables shipped to River Cottages and Y represent the number of tables shipped to Oceanside Resorts. Set up an objective function. Okay, before we do that, we got to read the problem here a little bit. So let's go back to the problem actually. Industry City is able to produce and send at most 400 tables to these clients. Okay, so that's another constraint. So let's deal with that here in a minute. So we need to interpret that here in a minute. It costs $80 per table to ship to River Cottages and $60 per table to ship to Oceanside. So now we know the shipping costs. So we can actually fill that out as we go. So right here it says it costs $80 per table for River Cottages. Okay, so River Cottages is $80 per table. Okay, and it also says $60 per table to Oceanside. So as we read the problem, we can fill out the table a little bit, right? I mean, it's not that hard. This is the easy part actually. All right, transforming them to inequalities, that's the more challenging part. Okay, it also says in the return for the purchases, all right, River Cottages has agreed to give Industry City $20 in rebates. Okay, so let's talk rebates here for a minute. So let's see, River Cottages has agreed to give Industry a $20 rebate. So right here, there's the rebate for each purchase. So as River Cottages gets the tables or shipped tables here, it's going to give a rebate back to Industry City, who's produces these picnic tables. And so the rebate to that River Cottage is going to get, it says, is $20 rebate. Rebates is a credit. That means money that goes back to the company right here. So we know that. And then it says for Oceanside gives $30 in rebates back to Industry City. So again, these are rebates. Okay, so you just interpret that and then it's get organized in the problem. Okay, now let's read on. So what does it say? It says the owner of Industry City, the main company that produces these table sets, has determined that the company needs at least $2,400 in credits, rebates, credits and rebates, to keep the shipping costs down. Okay, so it needs at least. Okay, so that's going to be constraint because we've got the words at least here indicates that we have a minimum number here, so this represents a minimum, and we're going to have to interpret that as a constraint in the problem. So we'll do that here in a minute. So that's going to be another one. So we have to interpret this one. Well, that's a dark color here, so let me choose a different one here. Okay, so that's going to be a constraint. Now the question is how many tables should be shipped to American and Oceanside to American? So that should be river cottages, and to minimize shipping costs. There's a little typo in here. Ship to river cottages and Oceanside to minimize shipping costs. So that's a typo. That should be river cottages. Okay. Okay, so how would we do that? How do we minimize the shipping cost? Okay, so our goal in this problem is to minimize, not maximize, but minimize the shipping cost. So we need an objective function that talks about the cost of doing things here. And to do that, we need some variables first. So let's go back to the workbook here and let's annotate a few things. It says let x represent the number of tables shipped to river, and then y represent the number of tables shipped to Oceanside. So let's do that. So let's define our unknowns. So x is going to be equal to the number of tables shipped, all right, to river. Y is going to be equal to the number of tables shipped to the Oceanside resorts. These are resorts. So you have to know what your variables represent, and even before you begin, because you don't know what to do unless you know what they represent. Okay, so x represents the number of tables shipped to river cottages, and y represents the number of tables shipped to Oceanside. Okay, so did part A. And then it says set up a cost objective function. Okay, so what we need to do is take the cost and write a function. So that means we've got to take these costs here and write the objective. Now objective means goal. All right, and our goal is to minimize, all right, the cost, minimize cost. So we need a cost function. Okay, so to do that, what we have to understand is that for every table that gets shipped to River Cottage, they cost $80. For every table that gets shipped to Oceanside, it costs $60. And what you're going to do is you're going to take the cost per table and multiply by how many that you're dealing with here. And we're dealing with X tables for river and Y tables for Oceanside. So you're going to need to take 80 times X and then add it to 60 times Y to get the total cost. So $80 per table times the number of tables, okay, cost times amount, so that's in dollars right here, plus $60 the cost per table times the amount for the tables that go to Oceanside. Okay, and that's going to be the representative of the total cost of the situation, and what we want to do is minimize that. That's the goal. All right, the only way to do that is to get to describe all the constraints here and then graph the system. Okay, but we got to read on. So let's read on. Okay, so part B here, it says in your workbook, write the river cottage's constraint inequality for the number of tables needed. Okay, so let's go back to the problem. Okay, so it says up here, let's go and reread. Okay, it says in the beginning, river cottages needs at least 60 tables. Well, check that out. Okay, that's going to go here, and then whatever that is. Okay, let's actually write it down. So if river cottage needs at least 60 tables, that means X, the number of tables shipped to Riverside, has to be greater than or equal to 60. All right, at least means greater than or equal to. So X has to be greater than or equal to 60 here. And if you look at the other one here, if you read on here, it says Oceanside Resorts needs at most 150. Well, guess what? So that one right there, if Oceanside needs at most, that means less than or equal to 150. That means Y has to be at most less than or equal to 150 here. So I just handled part B and C. Okay, so for river, okay, the number of tables has to be at least 60 tables. For Oceanside, they have to be at most 150, so less than or equal to 150. And we're talking about tables, obviously. Okay, so I'm using the workbook to help me out a little bit. I'm just trying to teach you how to use it. Now, in reality, like I said, I'm not going to give you all these tips and tricks right here. You're going to have to transform and read the problem and then interpret it by using the key language. Okay? I'm talking about the words at least, at most, and things like that. Okay? Those are key words in the problem. Now, part D, write a constraint or inequality for the total number of tables. Well, we talked about this in class. Total means sum. Now, if you're producing or you're shipping X tables to river and then Y tables to oceanside, then the total number would be X plus Y. All right, and it says write a constraint inequality for that. So if you read the problem here, it says in green. So let's focus in on the green here. This right here, this is the constraint inequality, and we're going to write it down here as well. Industry City is able to produce and send at most 400 tables. Now the words at most means less than or equal to. So this is going to be less than or equal to 400. So one of the major inequalities in the situation is X plus Y, which represents the total shipped, has got to be less than 400 tables. Okay. Now part E says write the constraint inequality for the credits. Okay, so let's talk about credits. So what are the credits? So let's go back to the problem. Now up here, let me switch colors here. We're talking about, so it cost, no, that's credits. So in return for the purchase, River Cottages has agreed to give Industry City $20 in rebates. So we're going to take these rebates here, credits, and apply it to our variables. Okay. Now for every table shipped to River Cottages, they're going to send back a credit of $20 to the company, and for every table Oceanside is shipped to, they're going to rebate $30. So what we need to do is we need to take our number of tables shipped right here, which is X for River, okay, and we want to multiply it by the rebate. So $20 rebate times every one of the ones that are shipped, plus, $30 is going to be multiplied by Y. So 20 times X plus 30 times Y, that's going to be, well, it's going to be what? Let's read here. So it says it needs at least $2,400 in credits. Look at that. So that's got to be at least greater than or equal to, all right, $2,400. Okay, and this is the rebate constraint. And that's what the book was talking about in part E. So in part E here, it's going to be 20 times X plus 30 times Y. That's going to be, it's got to be greater than or equal to 2,400 because it says at least. Okay, at least means that or more. So you really have to pay attention to the wording here. So we've got these two inequalities here. We actually have 4. So the other ones are already written up top. We have X greater than or equal to 60. We have Y less than or equal to 150. And we have our non-negative constraints too. X and Y both have to be greater than or equal to 0. So we have to take all of these, my friends, and graph them and find the feasible region so we can actually minimize the cost in this situation. So again, the objective or the goal in this situation, as stated earlier right here, the goal, all right, is to minimize the cost. Minimize that cost. Okay, so we got to write a cost function. So cost is equal to 80 times whatever X is plus 60 times whatever Y is. So we need to find the feasible region. Take a look at the vertices here and then substitute them in this objective function to find the minimum cost. The only way to do that is to graph the system. All right, so let's take these functions here and let's go to the graph and let's work on them. Okay, so let's write them down. So we've got X greater than or equal to 0, Y greater than or equal to 0. Those are the non-negatives. Okay, and then we have x greater than or equal to 60. We have y less than or equal to 150. Those are easy to graph. And then we have to graph x plus y is less than or equal to 400. All right, and then our last one here, we have to graph 20x plus 30y is greater than or equal to 2400. And again, you don't need Desmos here. As I've dealt with you guys in class here, we'll use Desmos to check, and we'll use Desmos at the end. All right, but we don't need it to graph. Okay, so let's first graph the inequalities. So first one, x is greater than or equal to 60. So you got to find 60 on the x-axis. So let me see. So half of 100 is 50. So it goes 25, 50, 75. So 60 is right about here. And so all x values that are greater than or equal to 60 lie to the right of this vertical line. So let's graph this. Let's sketch this. Okay. And so all x values that are greater than or equal to 60 lie to the right of this. So this is x greater than or equal to 60. Now, if you weren't sure about this, and you let's say if you don't understand, what you do is you kick in a little Desmos action here. So I'm going to bring it up here right now and just show you guys. So x is greater than or equal to 60. Okay, now you'll notice that you don't see any graph, and it's because of the scale. So we're going to change the scale from maybe 0 to 100 so you can see this inequality, and now you can see it. So notice that it shaded the regions to the right of 60, which kind of makes sense. Okay, so that's what I did first. Now the next one here, let's graph y less than or equal to 150. So this is the second one here. And now all the y values that are less than or equal to 150 are underneath this line right here. Okay, so here, y less than or equal to 150. Okay, they lie below this line here. And then, okay, and then now the third one here. So, I'm trying to use different colors here. So the third inequality, here you got to subtract x and get it in slope-intercept form. So we have y less than or equal to negative x plus 400. All right, notice the slope's negative 1. And I've talked about it in class that when you see this and your scale is 25 and your slope is negative 1 over 1, okay, it's kind of hard to handle. So we talked about in class how we can change negative 1 to any form we want. We have a y-intercept here of 400, so I'm going to start up here. Okay, now the scale is 25, so I can write this as negative 25 over 25. I can write it as negative 100 over 100. All right, so negative 1 is the same as negative 100 over 100. You simply multiply this fraction by 100 over 100. Or you can multiply it by negative 400 over 400. You can do that too. But if you go down 100 and right 100, you're here. Down 100, right 100. You can just plot these points and then graph your line. So take your straight edge out. And then draw your line. Okay, now the inequality is less than or equal to, so the solutions lie below. So I just graphed the y is less than or equal to negative x plus 400. And notice I'm labeling everything as I go. All right, and now I have to handle the fourth one here. So let's work on this one. So on this one here, I need to solve for y here. Get it in slope-intercept form, as they say. So let's subtract 20x. And I get 30y is greater than or equal to negative 20 times x plus 2400. And then divide everything by 30. What do we get? We get y is greater than or equal to negative 2/3, to simplify, x plus 80. All right, 240 divided by 3 is 80. So your slope here is negative 2/3. The y-intercept is 80. So we got to start at 80. So let me see. So 80, we got to be careful here. So let me see, this is 25, 50, 75. So 80 is a little bit above 75. And then we have to interpret the slope. So we got to be careful on this one. Well, I can multiply the slope by 40/40ths, and that will help me. That'll give you negative 80 over 120. So I go down 80, right 120. So down 80, right 120, right about here. That's close enough for government work, as they say. So let's graph that line. That's close enough. We'll use Desmos to verify everything. And because it's greater than or equal to, this is going to open up. The solutions here are above. So we shade above. So we got to go up this way. So this is y greater than or equal to negative 2/3 x plus 80. Okay. Now we're rocking and rolling. So now we shade in the, and then we, I got to graph the non-negative constraints. So the non-negative constraints, right here, we got to graph these guys. And so if y is greater than or equal to 0, then you're above the x-axis. Okay, this is y greater than or equal to 0. X greater than 0 is already satisfied because I already know that x is greater than or equal to 60, so that covers that one. So we got to be above the x-axis, to the right of this green line, underneath the purple one, underneath the blue one, and above the x-axis, and above the red one. So where they all overlap is called the feasible region, and it's in here. Okay. And it's, look at this. How many sides does it have? 1, 2, 3, 4, 5 sides. It's a 5-sided figure. It's a pentagon. Okay, not a regular pentagon, but it's a pentagon. Pentagon, it just means 5-sided figure. Okay, penta meaning 5. So it's a 5-sided figure and it has 5 vertices. Okay, so we need to find them. So let's just name them. Okay, so V1, V2, V3, V4, right, and V5. And so if you don't know exactly what all these are, you can use Desmos to verify. So use, all right, Desmos, all right, to verify vertices. Okay, so let's do that. Let's just make sure everything's correct. So let's put our functions in. Okay, so here we go. So x greater than or equal to 60, y greater than or equal to 0. Next one, y less than or equal to 150. Okay, and the next one, I'm just looking here, x plus y less than or equal to 400. Next one, 20x. Notice that I'm putting the original functions in. Plus 30y is greater than or equal to 2400. Okay, so now let's look at this and let's see what we got. Now we're going to have to change the scale here because the y-intercept of the fifth one here is 400. So I'm going to go and manually change that. So we're going to go from 0 to, let's go to 450. No, excuse me, got the wrong axis. Let's go to 100 here. Let's see if that's enough. Actually, let me look at the graph here. On the x-axis, we got to go from 0 to 4. Yeah, we got to go 0 to 450. So let's put in 450. On the y-axis, the same thing, 0 to 450. All right, let's see if we can see this. All right, we can. Okay, so let's click on the vertices. Look at that. So, there's something wrong here. Something's wrong. I didn't enter something correctly. What did I mess up? Where is my mistake? Something's not entered correctly here. X greater than 60, y less than 150. Oh, right here. I put 3y, not 30y. See, that's why you always check your work, people, because even I make mistakes once in a while. In fact, I make them all the time. All right, so I fixed the function there. Let me go back to the graph, and let's see if this all makes more sense. Okay, so there are the vertices, and my friends, there they go. Let's see if these make sense. Let's say they actually are the same as what we came up with here. So let me bring this into our lesson here, and let's compare. All right, so here we go. Let's compare. So what are the vertices here? So V1, is that really at 120, 0? And it is, because check out the position right here. So V, the vertex here, this is V1, V2, V3, V4, and V5. There we go. And those are the vertices up here on the graph. So we're going to take these 5 vertices right here, and we're going to use these in the table here. Okay, so here we go. So I'm going to take these right here. We're going to bring these into the first page, and we are going to optimize this problem. So here we go. So I'm going to just bring this in, and we're going to write these down. Okay, so here we go. Let's write them down. So V1, okay, that's 120, 0, 120, 0. V2 is 60, 40, 60, 40. V3, 6150. V4, that's 250, 150. And then the fifth one here, 400, 0. So once you write down all your vertices here, then you can get started, maximizing or minimizing whatever you're trying to do. In this case, we want to minimize the cost. All right, so what we're going to do is we're going to use Desmos here to our advantage. Okay, so each one is going to yield a cost, and what we want to do is find the minimum. So we're going to use Desmos for that. So here we go. So let's keep this in our sights right here, and let me whip up Desmos on the third line. Let's put this side by side. All right, so what's going on here? So let's add in a table. Let's put the vertices in. So 120, 0. Second one, 60, 40. Third one, 6150. Fourth one, 250, 150. And then the last one, 400, 0. Now in the third column, you write your objective function. So it's going to be 80 times, all right, times x1, because the variables are in x1. Let me just change something here. There we go. So 80 times x1, so type in x1, plus, all right, 60 times y1, so 60 y1. There we go. And notice that all the costs are generated. So let's go ahead and record these. So we have the following costs. So the first one is 9,600. Put a dollar sign on these because these are obviously numeric or currency here. The verse is 7,200. Third one, 13,800. Fourth one, 29,000. And fifth one here, we got 32,000. And you're trying to minimize the cost. So minimize means the smallest. All right. So what is the smallest? Well, it's obviously, all right, 7,200. So there's your minimum cost. And it occurs when you do this. So you have to interpret this in your optimal solution. So what does that mean? So let's go back to the original problem and look at our definitions. Now, so if you look up here at the upper left, X is the number of tables shipped to Riverside, River Cottage, y is the number table shipped to Oceanside. And so x is 60, y is 40. So you always look at your variables. All right, when you state the optimal or best solution here, you have to understand what x and y means. So x is 60, and that means we should ship 60 tables to River Cottage and 40 tables to Oceanside. All right, so the company should send, right, 60 tables, because we're talking about tables here, all right, to River Cottages. Okay, and 40 tables to Oceanside, all right, resort, to minimize the cost, which happens to be right here $7,200. All right, and that, my friends, is a full-blown programming problem. Okay, so what you need to do, again, just go back through it here, and you need to make sure that you guys fully understand this. So if you have to listen to this again or rewind and listen to any portion again, then do it. It's a video, for God's sake. So go through it here and make sure you can do it on your own, okay, without looking at the directions in your workbook. All right, so do your best, practice, and I'll see you in my next lesson. This is Aynesworth. I'll see you then. Bye-bye.